Hey everyone, welcome back to my channel. So today we're diving into the matchmaking system, specifically why having matchmaking on the client side can be, well, problematic. So for those who don't know what matchmaking is basically a system that pairs you up with thousands of players in rooms, determines like which room is a better fit to you. So in our case, it's just a regular joining room operation without any background logic. So so let's discuss the modifications that I made. So I implemented the challenge system, but we can get into that a bit later. So first and foremost, what's the drawback of having the matchmaking system on your client is security. So when matchmaking is handled on the client side, it becomes an open invitation for hackers. So with direct access to the matchmaking process, it's easier for them to manipulate the system, leading to unfair matches or even security breaches or SQL injections and so on and so forth. So, but the biggest advantage of it is that you delegate the load from the server to the client. The inconsistency can also happen. I mean, if you update, so let's say update your client on your source, so if the clients are not like the same version, then the logic can differ. Or if so, machines basically clients machines can be different, so different computational speed. So the matchmaking can also be affected on that as well. So one can join a room in a minute, and also one in 5 minutes. The machine is pretty low, pretty slow. So, but yeah, but initially I just implemented it with the idea in mind of delegating the load from the server to the client. So all these issues and disadvantages can be solved, but this is pretty tough. And I'll start from uh, malicious client attacks, reverse engineering that can happen on the client side regarding the matchmaking. So I'll just try to go through the code and explain you what can happen on the code. So I modified the message.proto. I added a function, RPC function that's called solve challenge, and modified the heartbeats response. I added the challenge question. So this challenge question, what's that? So challenge is actually a task that is generated or that's already in the server that's awaiting for a proper correct response from the client side to be able to validate the client. In case the response from the client is wrong, the client is immediately deactivated, deleted from the server. So that was the idea behind having the client on the local machine. But the problem is that so this challenge thing I implemented it somewhere here. Solve challenge. So here I hard coded the challenge response. So the request is like 1 to 3, 1 plus 3. I guess it's 1 plus 3. Yeah, 2 plus 2. So it's 2 plus 2 the question, and the response has to be 4. Has to be returned 4 from the client side in order for the server to validate the user. So it's basically a raw. It's a raw answer. It was supposed to be different. So basically, I sought to implement the the system that's called client integrity validation. basically when you're making connection requests from the client side on your local machine to your server, the client was supposed to create a sort of snapshot of the code base of it. So by using SHA-256 hashing algorithm. But in general, the idea is pretty cool. You can, before running a client, for dialing up the gRPC server, the client can generate its snapshot. It can be fairly light, and return it to the server for the server to validate it. But the problem is that it's still inefficient, and I'll tell you why. So just imagine you have a client on your machine. It's already compiled, it's already built, it's already in a binary format. So if hacker wants to hack your system, if I may call it this way, in simple words, he'll just reverse engineer the client side, get rid of the part that generates the hash, generates the snapshot of a client, and will keep the initial client because he knows that the initial client snapshot is the one that's on the server side, the one that's valid. So he can change the code, he can remove some parts of it. Let's say the generation part is here. Generate client snapshot. And somewhere in here's like pass client or validate client snapshot. So I can literally delete this part, keep the validation, keep the file, the snapshot somewhere in the folder hierarchy, validate the client, change the code, and start making malicious requests. That's the problem. It's actually very hard to tackle with it. I mean, to be able to implement such a system. So I just wrote it in my recent LinkedIn post. So that would be ideal if this GRPC dial, had an ability to kind of catch the code that it's running from. In our case, it's main.co. Would create a snapshot itself, but in a like pretty secure way, and send it in package in sockets. And if we could catch the sockets on the server side, if we could catch the code base snapshot on the on the server side, then that would be pretty efficient. In this way, we'll definitely validate the client on the snapshot without having the snapshot saved in the folder hierarchy. It can be easily retrieved. But unfortunately, we don't have it. So it's a topic for later discussions. So for now, I'll keep the local client as a topic for research. Maybe I'll find something that can implement such a thing, like in a highly efficient and secure way. I mean, having the dial, so having such feature that makes a snapshot of the client of the code that the dial function is calling from. So, and passing this snapshot in sockets, but that's actually yet to be researched. So for now, I will move the matchmaking side from the client to the server side. That won't be that long. Basically, it'll just, whenever it'll create rooms, client will create rooms and something. So here we're directly accessing the Redis database. We're creating rooms, we're modifying them, we're deleting them. So this whole operations will be shifted to the server side, and the create room, leave room, and all other relevant functions will be just making calls to the server side by providing some details, and then the server side will decide whether the requests are actually valid or not. Yeah, that can create an extra load layer, but the load shouldn't be actually that big because the communication is so the room handling, room management is happening in Redis. Redis is Redis is actually an in-memory database that has a high throughput, so it shouldn't be that big of a deal. I mean, having requests from client or server to the Redis back from Redis to client is pretty fast, so that shouldn't be a problem. So the modification made were in here, message of Proto. I haven't pushed the modifications to the GitHub yet. I'll do it later by today. The challenge response, solve challenge. It has the it has only one attribute, which is question, and challenge response is the answer. You can play around with it. You can create your questions, your responses. So maybe you can find a better way to handle all this client matching problem. Maybe you'll find a way to encrypt the client snapshot into the gRPC dial function. So apart from that, I think I already told you about the validation on the server side. Ah, yeah. So in this lines, I just explained it in the previous tutorial. We're providing the server, getting the server address, the application ID from the terminal. Then we pass it to the appropriate functions to check whether they exist in the database, and if they exist, then we proceed. But that also has its own drawbacks, which is again the same problem. I mean, the code can be easily reverse engineered if the code base is not, the binary is not encrypted well enough. And these things can be changed, right? They can be easily deleted. They can be easily deleted. Yeah, so which will definitely lead to unexpected uh, system behavior. So that can be also protected in some way from the server side. I'm just thinking on how to deal with this problem. I'll figure it out later. So that was the change that I made so far. So basically now you see the idea. I'll run the project to show you how this check validation works. So as I showed you, the main.go has two functions. Solve challenge was lowercase s and capital case S. And the one with the capital case S is the RPC function that is defined in here in the proto. That is a function that is running both on the server side and the client side. It has the other function that is lowercase solve challenge. Lowercase solve challenge is just an auxiliary function that helps to terminate the user in case the validation didn't go through, and just terminates the whole routine. the whole go routine, main routine, once the validation is failed. So in here, it's happening in here. We get our response. We send the heartbeat. I also modify the heartbeat part. I think it was now the response. Yeah, the response has changed. So response has the heartbeat response now has the challenge question. We get our challenge question. Our challenge question in here. If the challenge question is not null, then we try to uh, solve the challenge question. If it's solved, if it returns true, then we just go through this if and we carry on the loop. But if it's not true, it's false, then it means that the challenge actually failed. So then we just send the true message to the done channel, which is the channel that's connecting the main routine, the main go routine, and running here. If done is detected, if done has a message, then we're terminating the whole process. We, as you can see, we just exit the whole program. So the client also terminates. So, but this part is working well. I mean, even if it's reverse engineered, the client is reverse engineered. And this lies for solving the challenge. Also deleted or modified as long as the server gets the valid answer. The client will be able to make messages to the server. If it fails, if client fails to send the proper answer, the correct one, server just deletes the client from the client list. So even if client tries to send messages after failing, the server won't take this request into account. It won't broadcast the messages among the clients connected to it. So it's in here, in the check heartbeats in here. And we get our challenge question. What's 2 plus 2? Just hard coded. So we pass the challenge question to the challenge client. So to the challenge client function along with the client info, which is the pointer to the actual client. So if it returns false, and we just say that client failed the challenge. We put it into the message variable. We pass it to the remove client, and the remove client in return try to check whether the user is in the room or not. If not, it just deletes it. So in this part, we just delete from the hash map. We delete the address, the user address, the client's address. So if now client wants to make some messages, some RPC calls on the server side, he will, but the client won't actually broadcast. As I said, won't broadcast these messages to all those clients. We can take a look at it in here. So broadcast messages. As you can see, here we check whether the client info RPC call is not null. If it's not null, then we broadcast the message. If it is null, then we just pass through the loop to the next iteration. We just ignore the messages. So the messages will be just simply ignored. So that part is secured. So the remaining ones are the challenge part. So challenge, I mean the snapshot part, which is kind of strange. It's kind of ambiguous. So there should be some other more flexible implicit mechanism, highly encrypted, to be able to solve that issue. But for now, I will just, as I said, move the matchmaking to the server side. So it will have the PulseCore will have two methods. So client that is using matchmaking on the client side, and another client that's using matchmaking on the server side. So you can play with it as well. Maybe you'll find some more fancy solutions to it. So that was for today. Thank you for your attention.